What we have seen earlier was a Dijkstra algorithm, that is single source shortest path. Starting from one vertex, we visit all the other vertices. But now we are going to talk about all source shortest path. This is known as Floyd-Warshall's algorithm. In case of Floyd-Warshall's algorithm, you can imagine that indirectly we are applying the Dijkstra algorithm for each and every vertex. Right? So in the background, you need to identify that what is the minimum path required from one vertex to any other vertex, and not required just from the source vertex, but from any arbitrary vertex to all the vertices. And there is one more thing, that this particular algorithm does not work for the negative weight cycle, right? So in this case, we can have certain edges with negative weight. But when we talk about negative weight cycles, I'll give you an example that whenever there is a cycle inside the graph, let's say there is a directed graph or undirected graph, and whenever there is a cycle, right, we have seen that cycle is simply a path that we follow. We start from one vertex, and by visiting the set of vertices, we come back to the same vertex. So if there is a negative weight cycle, then Floyd-Warshall algorithm does not give you a solution. So we'll start with an example, and this particular algorithm is going to follow the dynamic programming, in which we are going to identify all the possible combination to get the answer. Therefore, this is going to take much more time compared to this Dijkstra algorithm, but this Floyd-Warshall algorithm is preferred when the particular graph is dense graph and you are going to have a negative weight. So Dijkstra algorithm does not work for negative weight. However, Floyd-Warshall algorithm can also work for the negative weight. So what we are going to do is, let's say that we have n number of vertices. So to identify the all source shortest path for n number of vertices, we create certain matrices, and number of matrices will be equal to number of vertex plus 1, that is n plus 1, starting from 0 and going to n. So whenever we need to identify the path from I to j, what we are going to do is, we are simply going to add the corresponding weight, and whenever there is no path, so no path exists, in that case we write down infinity. So let's consider this graph. You can see that this is a directed graph, so this can work for both directed and undirected, but make sure that it has to be a weighted graph. Even Dijkstra algorithm can work for directed or undirected graph, but the difference is it cannot work for negative weights. Here you can see that we have certain negative weight edges. So from 1 to 3, you can see that the path from 1 to 3 is going to have weight as -2, and from 4 to 2, we have weight as -1. So now let's see that what is the negative weight cycle. Here you can see that I do not have any cycle inside the graph. But let's say that I have a path from 2 to 1, then from 1 to 3, and let's say there exists a path from 3 to 2. And consider that for the instance that the weight is -3. So when you identify the cycle 1 to 3, 3 to 2, and 2 to 1, consider this weight as -2, here -3, and 4, then the total weight will be equal to negative. So this is known as the negative weight cycle. But here there is no cycle, and even if there is a positive weight cycle, Floyd-Warshall's algorithm works fine, but there should not be any negative weight cycle, right? So let's see how does it work. So I have already told you that we need to create n plus 1 number of matrices starting from D0. Now here number of vertices are 4. So I'm going to create 5 matrices, D0, D1, D2, D3, and D4. I'll tell you what is the significance of all these matrices. Let's start with D0. So D0 simply gives you a formal representation of a graph in the form of a matrix. We need to identify that where is an edge from one vertex to another vertex. So this is n by n matrix. You start with 1. From 1, identify the number of from 1, identify the edges from 1 to 1, 1 to 2, 1 to 3, and 1 to 4. So you can see that the diagonal elements are 0 because this is not going to have any self loop. So no self loop is present. Therefore, from 1 to 1, the weight is 0 because if you are at 1 and you reach 1 at that particular node. So 1 to 1, no cost will be required. Therefore, all the diagonal elements are 0. Now you identify weight from 1 to 2. So this is a directed graph, right? We have an edge from 2 to 1, but there is no edge from 1 to 2. So if there is no path from 1 to 2, we simply write down infinity. So there is no direct edge. Therefore, the path from 1 to 2 is infinity. Similarly, you can see the path from 1 to 3. So there is a direct edge. The cost is -2. So we have written the corresponding weight. Now there is no direct edge from 1 to 4. Therefore, 4 is not reachable from 1 directly. We have written infinity. Similarly, we complete the matrix. You start with 2. So from 2 to 1, there is a direct path. The weight is 4. 2 to 2, diagonal elements are already 0. 2 to 3, there is a weight, that is 3. And there is no edge from 2 to 4. We are talking about a direct edge. So no direct edge exists from 2 to 4. So 4 is not reachable, therefore infinity. Similarly, go for 3. No path from 3 to 1, infinity. No path from 3 to 2, again infinity. 3 to 3, a diagonal element will be 0. 3 to 4, the weight is 2. So we have entered 2. Similarly, for 4, from 4 to 1, there is no edge. From 4 to 2, the weight is -1. From 4 to 3, the weight is infinity because no direct edge present. And from 4 to 4, this is a diagonal element and therefore it is 0. So this is just a simple representation of a matrix. Whenever there is an edge, identify the weight, note that weight and add it to the matrix. Whenever there is no direct path, simply write down infinity. And just because this kind of matrix do not have the self loop, we write down 0 in the diagonal elements. So this is how D0 is filled. Now the next thing is how we are going to proceed to get D1. So before we start filling D1, I have written some instructions on the right hand side that the rest of the table, that is D1, will be now dependent on the values of D0. So let's say I need to identify D1, let's say any value I comma j. So this is given by a formula. We need to identify minimum of D of k minus 1, that is from the previous matrix, identify the value at the same location, or considering k as an intermediate node, identify the path from I to k and then from k to j using the previous matrix. So let's fill it. 1 to 1 is 0. Now this 1 represent that we are going to consider 1 as an intermediate. So if I consider 1 as an intermediate, one thing will be very obvious, that all the values corresponding to the row 1 and column 1 will be as it is because we are taking 1 as an intermediate. But still, if you have any confusion, we can proceed. So 1 to 1 is 0. There is no change in the diagonal elements throughout this process. Identify the value from 1 to 2. So put I is equals to 1 and j is equals to 2. And the value of k is 1. So d1, 1 comma 2 will be equal to minimum of d of k minus 1, that is d0, 1 comma 2. So identify what is the value of 1 comma 2 in d0. It is still infinity. See the second option. I need to identify the value from 1 to 2 by considering 1 as an intermediate. So you identify 1 comma 1 plus 1 comma 2 from the previous matrix. So you can see that directly or indirectly we are getting this 1 comma 2, and the value for that 1 comma 2 was already infinity. So there is no change when we talk about the first row. Similarly, when you check for the first column, all the entries will remain as it is. So whenever the value of k is 1, the row corresponding to 1 and column corresponding to 1 will be as it is as of the previous matrix. So there is no change. So we are directly going to start with 2 comma 1. So for 2 comma 1, apply the formula. You will get the same answer because we are inside the same column. So I'm not going to check that. We will directly go to 2 comma 3. So to calculate 2 comma 3, identify the minimum of 2 comma 3 from the previous matrix. So previous matrix has the value of 2 comma 3 as 3. Then identify the value of 2 comma 3 by taking 1 as an intermediate node. So identify 1 as an intermediate node. I will break this problem of 2 comma 3 to D0 2 comma 1 and then D0 1 comma 3. So D0 2 comma 1 is 4 and D0 1 comma 3 is -2. Add this value, this will give you 4 minus 2, that is 2. And the value that we have got for the first component, that is D0, 2, 3 is 3. So the minimum of 3 and 2 is 2. Update the table. So 2, 3 will contain value 2. Similarly, check for 2, 4. So from table D0, 2, 4 was infinity. Break this path of 2, 4 by considering 1 as an intermediate node. So path from 2 to 1 and then from 1 to 4. So path from 2 to 1 is 4 from D0 and path from 1 to 4 is infinity. So infinity plus 4 will give you infinity, and therefore minimum of infinity and infinity will remain infinity. Similarly, go for 3, 2 because 3, 1 we are not considering here because the value of k is 1. So corresponding row and column will have the same value. Identify 3, 2. The value of 3, 2 from the previous matrix is infinity. Break the path of 3, 2 by considering 1 as an intermediate node. So identify path of d of 3, 1 and then 1, 2. So d of 3, 1 is infinity, right? Do not need to look for the second option because infinity plus infinity will give you infinity again. Therefore remains as it is. Similarly, go for 3, 4. 3, 4, check the value. From D0 we are having 2 and then break the path 3, 1 and 1, 4. So 3, 1 is infinity. Infinity, whatever you add will remain infinity. So minimum is 2. Similarly, we need to fill up the table for 4. Infinity remain as it is because this is the first column. Now identify the value for 4, 2. From previous table we are having -1. Break it into 4, 1 and 1, 2. So when you break this, you will get 4, 1 as infinity. No need to look further. So -1 is minimum. Similarly for 4, 3, from previous case we are getting infinity. Break this 4, 1 and 1, 3, but 4, 1 is already infinity, therefore remains infinity. This is how we fill up the table for D1. Similarly, when I go to D2, this is how we are going to fill up the table. So for D2, what you are going to consider? You are going to consider D1 as the base table. Considering this as a base table, when we identify I, j, the value of k will be 2. So now throughout this particular process, we are going to consider 2 as an intermediate node. So what we will do, the value corresponding to row 2 and column 2 will remain as it is. Identify the path from 1, 1. So the 1, 1 from previous table is 0. Break the path of 1, 1 by considering 2 as an intermediate. So 1, 2 and then 2, 2. So 1, 2 is infinity. Therefore 0 is minimum. Similarly, identify for rest of the tables and the final answer will be in case of D4. This is how we proceed. I'll give you the example, and with the help of example, you can see that this is going to give you the final all pair shortest path.